Let's review some work energy concepts that you'll need to know for your upcoming energy quiz. The first concept that you need to know how to describe is whenever a force does work. When forces do work, they cause changes to your system. So the way we measure work is we take the magnitude or the strength of that force, we multiply it by the object's displacement in a particular direction, and then we have to multiply it by the cosine of the angle, whereby the angle represents the direction of the force relative to the motion. So we want to take a couple quick examples that we've covered before in class. Take a box at position 1, it moves to position 2. It covers a displacement delta x, and in case 1 we apply a force on box at position 1 straight to the right. Because F and delta x are in the same direction, the angle is 0, the cosine of 0 is 1, so the work done by that force is whatever the value of that force is times the displacement. You find out that when the force is in the direction of motion, you get the maximum positive work done that that force can do. Take case 2. So on the box at position 1, you begin to apply a force that is upward. At the same time, the box is moving to the right. We'll cover some displacement. This angle here now is 90 degrees. The cosine of 90 equals 0. So it must be true that the work done by that force is 0. And it makes sense that a force that is pulling the box up can never cause motion to the right. So in this case, hypothetically, maybe the box was already in motion on a nice frictionless surface and just continues to move. If there was friction, we would expect the box to slow down. That's not our concern. That would be due to friction, which is not a force that we are trying to describe here at this point. We're just focused on the force that we applied upward and asking the question whether that force did any work. The third case is if I take the box at position 1 and I apply a force up at an angle. And usually that angle is measured from the horizontal. And I can give you any angle here, and so you'd have to be able to calculate what that angle would be in the cosine function, and so the work would be F times delta x times the cosine of that angle. So let's take an example. Let's say F equals 10 newtons and delta x equals 5 meters, and let the angle be 60 degrees. The cosine of 60 is 1/2. So F, which is 10 newtons times delta x, which is 5 meters, times the cosine of 60, which is 1/2, equals 25 Newton meters. So that's how much work that force does as the box moves 5 meters across the floor. Notice again in this example that if I were to decrease the angle to 0, then we come back to this case. Since the cosine of 0 is 1, then the amount of work done by that force would just be 10 times 5, which would be 50 Newton meters. So the force would effectively be doing more work. You're exerting the same force, but now more of that force is in the direction of motion, and so therefore we say that it does more work. And again, the value is positive, so we can also say that that force has done positive work. We take that same force, that 10 newtons, but we apply it straight upward. Cosine of 90 is 0. So despite the fact that you're applying that same force, the box moves the same distance, the work done by that force would be 0. The last case is if I were to apply a force to the left while the box moves to the right. This angle here, theta, equals 180 degrees. The cosine of 180 degrees is -1. So if we use the numbers from the last example, the work done by this force would be -50 Newton meters. It'd be 10 times 5 times -1. You get -50 Newton meters. So here the box is still moving to the right, but because the force opposes the motion, then we would say that that force has done negative work. So work is a scalar quantity. It does not depend on direction, but you do have to know the relative directions of the force and the direction of motion. So this negative doesn't necessarily tell me that it's moving to the left or to the right, but it tells me that the force is opposing whatever motion the object has, and that's the difference. Vectors, if it was a vector quantity and it was positive or negative, it could tell me whether it's moving to the right or to the left. But I don't know for sure if this object is moving to the right or to the left, because if I took the case where we were moving in this direction from position 2 to position 1, then, and let's say I apply a force to the right and it covers its displacement to the left, you still have that angle. Theta is still 180 degrees. Cosine of 180 is still -1. The values of the force and the displacement may be the same if we use the same numbers, and so you'd still get that the work done would be -50 Newton meters, but now it's moving in a completely different direction. But what's consistent of these two examples is that the force is always opposing the motion. So that is when a force does negative work. It must oppose the motion. So you can expect to see a couple of questions where you identify a force in a situation and you're asked whether or not it does any work at all, and if it does work, whether the work is positive or negative. So if the force is helping cause that motion, it's in the direction of motion, it's doing positive work. If it's against the motion, it's doing negative work. Okay, so the next idea is how work relates to energy. And here we had originally described the fact that the energy is what gives a force the ability to do work. So we assume that if forces are doing work, that they had energy. And it's a nice way for us to keep track of the amount of work that these forces are able to do, because we would say that there is not an unlimited supply of energy in a system. So if you can calculate how much energy the system has, then you know how much work can be done and how much change we can get from any given force in our system. So here we have a system, and if you recall, we began using pie charts to represent the amount of energy inside of this system here. So that energy bubble represents the amount of energy in our system. So if you have forces doing work, they're interacting with other objects. One object is pushing another object across the floor. Objects are dropping. Objects are compressing springs. All right. These forces are all causing changes. They're all doing work. They all require energy. But the energy was already in the system. So despite the fact that the work is being done in here via these forces, the energy that they're using is just being exchanged from one object to the next. So the total energy of the system remains the same. So that's what we call conservation of energy. The energy might change forms, and so we'll talk about that in a moment, the different forms of energy. And so you can get different types of energy filling up this pie in different percentages, but the total amount of energy in this pie remains the same. Unless you have a situation where you have another system out here that has energy and it interacts with your system, right? So if this system does positive work, then it helps deposit new energy to our system. So this system loses energy, and this system gains energy. And so the way we would represent that is our pie gets a little bigger. You can see that. If there was another system over here, and now this system does positive work on the other system, then the energy that we once had here transfers over to this system, and so now our pie gets smaller again. So if any new energy enters into your system, you know that that was the result of work being done by an outside force. If you all of a sudden lost energy in your system, then you know that you must have been doing negative work, or you were doing positive work on another system. Okay, so if you do positive work, another system can be doing negative work, and that's how you might be losing energy. So the types of energy in our system might come in the form of kinetic. Remember, kinetic energy is the energy of motion. We learned that to calculate kinetic energy, that's 1/2 mass times velocity squared. So the faster objects are moving, the more kinetic energy they have. And mass is also a factor. So the more mass an object has, the more kinetic energy they can carry as well. Okay? So if an object's moving with constant velocity, they have kinetic energy, but the amount of energy that they have remains the same. If an object is accelerating, if they're speeding up, the amount of kinetic energy that they have must be increasing, and that must be due to the work done by an outside force. Okay? If it is an inside force, then we already knew that system had energy in a different form. So that's where the storage forms of energy or potential energies come from. And so one form of potential energy is gravitational potential, and that's a function of height, specifically change in height. So to calculate gravitational potential energy, you have mass times the gravitational field strength, little g, which you can use 10 newtons per kilogram for that. And again, this just represents the force of gravity. And then I'm going to use the letter h, and really h means the change in the height. So it's wherever your starting height is to wherever your end height would be. So the way we had come up with this formula was we found that a particularly nice type of graph was a force over a displacement curve. So if you were to plot force over a given distance, then what we learned is if we found the area under the graph, it gives us a couple pieces of information. For one, it gives us how much work has to be done in order to cause that change. And when you're plotting a conservative force like gravity, if this is now, for this example, Fg, where over a given height, the force of gravity doesn't change, then after I get to some height, by finding this area, that's the amount of work that I would have to do to lift that object to that height. If I'm doing positive work to lift, gravity is doing negative work. When gravity does negative work, it stores energy. Conservative forces store energy when they do negative work. So here we're just seeing the strength of gravity. But if I know I'm lifting this object from some initial height to some final height, then I know gravity is working against me and it's doing negative work. So all of this work that I'm doing, which I can find by finding the area, translates to the amount of energy stored by gravity, and that's the gravitational potential energy. And so the length times the width of this rectangle gives us our mgh. The next form of energy that we learned about was elastic potential energy. As a side note, we did the spring lab and learned a little bit more about the spring force. This delta x here represents the amount of stretch or compression that the spring experiences. So that's how springs store energy, is when you stretch or compress them. And we learned that the more force you apply on the spring, the more it pulls back. The spring force is always a restoring force. So if you apply a little bit of force, you get a little bit of stretch. If you apply a lot of force, you get a lot of stretch. And it follows the unique relationship that the spring force
Mr. Costanza, you need to pay the contact man. Mr. Costanza, please go pay the contact man.
the spring force is a conservative force, and it's proportional to the displacement of the spring. And the constant of proportionality is the slope of this graph, and we call K the spring constant, which represents how tough the spring is. It would have units of newtons per meter. So the more newtons per meter the slope is, the more force it takes to stretch a spring a given amount. So it must be a tougher spring. So this equation here represents the strength of the spring force. We call this Hooke's law. If you wanted to be specific about direction, we sometimes add a negative in here to show that it's always opposing the motion of any force that you apply. But I'm going to leave it without the negative at the moment. The area under this graph represents the amount of work that I'd have to do to stretch the spring by a certain amount. But while I'm stretching it, if I'm pulling a spring to the right, then the spring is pulling back at me. So I'm pulling to the right, the block's coming with me, I'm doing positive work, the spring is doing negative work. When conservative forces do negative work, they store energy. So all this work that I've done by finding the area here is going to give me the energy that is being stored by that spring. And so the formula we came up for the elastic potential energy was 1/2 k delta x squared. So that comes from the area of that triangle. Half the base times the height, so half the force times the displacement, but you plug in k delta x in for the force and you get 1/2 k delta x squared. The last form of energy is EQ. Now EQ doesn't have its own formula per se, but in an example where you have a box that, as it was moving across the floor with some velocity, it eventually comes to a stop. How is that possible? Well, if we take the box and the ground to be our system, then we know that it began with kinetic energy. But since it comes to a stop, all that kinetic energy is gone, and so we still have to account for all the energy that the system once had, but the box no longer has it to use. So it must have been converted into EQ. So if I knew what the mass of this box was and the value of the speed, I can calculate the kinetic energy using this first formula. Well, once the box comes to a stop, all of that energy is now in the form of EQ. So now I know how much internal energy was lost from the box and is now in the ground. So how did that energy creep into our pie chart? So anytime there's a change in what's in these pie charts, a force is acting, but it's inside of our system. And that force in this case would be friction. Now friction is doing negative work. So just like when gravity does negative work, if you were to throw this box up in the air, the kinetic energy would drop, the gravitational potential energy would increase. Well, that's the same thing here. You're working against friction, so the kinetic energy drops and you get an increase in EQ. The difference is that when the box comes to a stop when you throw it up in the air, gravity takes the energy that it stored and uses it again, gives it back to the box when it does positive work. But once this box comes to a stop, friction goes away. It had no ability to maintain the energy that it robbed the system of. All that energy is now in the ground. Caused all the little molecules in the ground to jiggle, heat the air, move the air out of the way, cause circulations. So it is no longer in the box and no longer usable for our system. But because we know that the energy that we accumulated in the form of EQ was done by the work, the negative work from friction, then we can actually use that to determine a couple different things depending on what we have. Let's say we wanted to know how far this box traveled before it came to a stop. Well, since this is equal to the work that was done by friction, and work is F delta X, you'd have negative work, FF delta x cosine theta, but cosine theta is 180 degrees, so you'd get ff delta x. So if you plug in the value of friction and you knew how much energy you started with, which would have been in the form of kinetic, so you would have had kinetic energy that converted into EQ, then by dividing both sides by friction I could figure out how far the object would go before it comes to a stop. Okay, so one other review point, going back to our Hooke's law graphs, you should be able to look at two different graphs, two different lines on maybe the same graph. You should be able to come up with the equation that represents each line and describe what all the values in your equation represent. So take the case where you have this line and here you have this line. So each of these represents a spring. So this is spring 1, this is spring 2. So if I tell you that this value here is 2 newtons, and I tell you that this slope is 10 newtons per meter, and this slope is 5 newtons per meter, then what you should be able to tell me is what are the equations that describe both of these graphs. So for spring 1, F1 equals the slope, which is 5 newtons per meter, times delta x, and the intercept is 0, so I don't have to include that. For spring 2, it would be F2 equals the slope is 10 newtons per meter times delta x, and this one does have an intercept which is 2 newtons. So what do these equations tell us about these springs? For spring 1, we know that because it doesn't have an intercept, that means that any force that you apply on the spring will immediately begin to stretch the spring. Whereas in spring 2, because it has an intercept of 2 newtons, that means that you have to apply at least a 2 Newton force on the spring to begin with so that it can begin to stretch. So any force less than 2 newtons is not enough to begin to stretch that spring. Once you get it to that 2 newtons, then any force will stretch it after that. 2.1, 2.2, 2.3 newtons, but you have to at least apply a 2 Newton force in order to begin to stretch that spring. That's what we had called the loading force. Now, what do the slopes tell us? The fact that the slope for F2 is greater than the slope of F1 means that F2, the second spring, spring 2, must be a stronger spring. It is actually twice as strong. So these represent the K values. This is K2, this is K1. So if K2 is greater than K1, then K2, the second spring, must be a stronger spring. So it's harder to stretch. You'd have to stretch, in order to stretch spring 2 1 whole meter, you have to exert 10 newtons of force. So you'd be doing more work stretching it 1 meter than you would stretching a spring 1 by 1 meter, because you'd only have to apply a 5 newton force. But for the case of the springs, remember that in order to calculate how much work you have to do to stretch the spring, work is the area under the graph. So if you want to calculate the area, you have to use the area of a triangle. So half the base times the height gets you the area for that shape. In the next video, I'm going to go over some of the problems from worksheet 3.